Okay, welcome back everyone. In the last lecture, I tried to convey what the concept of confounding is, how it's a problem in epidemiologic studies. And now I'd like to take this a step more practical to make a definition that comes out of that concept. Well, remember this causal diagram that we left with last time. This describes confounding. We're looking at the effect of an exposure on an outcome. We looked at smoking in the previous example. We wanted to know whether it increased the risk of developing coronary heart disease, and we were worried about this other factor, age, that provided a backdoor pathway, another possible explanation why the smokers are getting more heart disease than the non-smokers. Well, from this diagram, we can come up with certain implications, and those implications can lead us to a definition of what a confounder is. So remember, a confounder has two properties. It has to be, in some sense, related to the exposure, and in another sense, it has to have an independent pathway, its own pathway, independently of smoking. Age is going to increase your risk of disease. Even if you're a non-smoker, the older you get, chances are the higher your risk of developing coronary heart disease. So looking at that causal diagram, we can make certain implications of what properties a confounder has to have. And there are basically two main properties. That arrow connecting the confounder to the exposure, age to smoking, says that a confounder has to have different distributions in the two groups you're comparing. I told you, for example, the smokers were much older than the non-smokers in the previous example. That's one property a confounder has to have. But that enough is not alone. Alone is not enough to make age a confounder. It has to have another property. It has to be related to the outcome. It has to have an independent relationship to the outcome, independent of the exposure, independently of smoking. Age has to have a connection to your risk of developing heart disease, your incidence of developing heart disease. It could be a risk factor or it could be a marker for some risk factor. Let's refer to that as the determinant of an outcome. It has its own influence in some regards on what the incidence of heart disease would be. And there's a third characteristic that's implied by that causal diagram. The causal diagram says that this confounding factor, age, was not a consequence of the exposure. It's not part of what we call the causal pathway. We're not assuming that smoking causes you to be old, and therefore old age leads to heart disease. We're not saying that age is part of this causal mechanism, the direct pathway connecting smoking to heart disease. It's a backdoor pathway. So these three properties of confounding are the typical ones you'll see in epidemiologic textbooks when they describe the definition of confounding. So let's make this our working definition, that a confounder has to have these three properties. And the first two, we can see if there's evidence for that in the data set. So let me show you that by an example linked to the one we talked about in the previous slide. So let's suppose this is the result of our cohort study. We enrolled 1,000 smokers and 1,000 non-smokers. We observed 240 cases of coronary heart disease occurring among the smokers and 120 occurring among the non-smokers. We can estimate the cumulative incidence, the estimated risk from these data, and we could say the estimated risk among the smokers, the cumulative incidence, will be 240 divided by 1,000, which is 24%. And among the non-smokers, it's 120 over 1,000, which is 12%. And from that, we can calculate our risk ratio. The risk ratio would be the risk among the smokers, 0.24, divided by the risk among the non-smokers, 0.12, which gives us that value of 2.0 we had. So let's suppose this is what we had in our cohort study. And then I went a step further. I broke this data into two groups that were young and old. Let's suppose there's a definition for old age, and we could debate what that might be. My personal definition for old age is probably much older than your maybe definition for old age. But let's suppose we took our 2,000 people, our 1,000 smokers and our 1,000 non-smokers, and broke them into two groups, those who were old and those who were young. And we looked into our data set, and we saw that among our 1,000 smokers, 600 of them were old, and 400 of them are young. Among our non-smokers, 200 of them are old and 800 of them are young. And furthermore, when I broke my data, it turns out that among those 240 smokers who got disease, 180 of them came from the old group and the other 60 from the young group. And among the 120 non-smokers who got disease, 40 of them came from the old people and 80 of them came from the young people. That's what our data showed. Now, can we use this table to help us decide whether age is a confounder using our definition, our working definition of confounding? It says age has to have different distributions among our exposed and non-exposed people. So let's see that. Does age appear to have different distributions in this data set? Well, yeah. We had 1,000 smokers, and the previous slide said 600 of them are old, so 60% of our smokers are old. We have 1,000 non-smokers, and 200 of them are old. That means 20%. So we can tell you from the data that the age distribution of our two groups is not the same. The smokers are much older. 60% of them are old compared to only 20% of the non-smokers. So it does seem to satisfy the first criteria for confounding. Age is related to your exposure status, your smoking status. The second criterion, the second component of that working definition that says age has to have an independent association with the outcome. Well, we can use that same data to answer that question, independently of smoking. So let's just look at the non-smokers. We have among the non-smokers 200 people who are old and 800 people who are young. What's the cumulative incidence of heart disease among non-smokers who are old compared to non-smokers who are young? Does it change when you move from the young to the old group? Does old age increase your incidence, increase your estimated risk of getting heart disease? Well, we see that among the young non-smokers, 80 of them got disease, 80 over 800, or 10%, will develop coronary heart disease. Among the old non-smokers, there are 200, 40 of them got disease, 40 over 200 is 20%. So notice your cumulative incidence doubles as you age from being young to old among the non-smokers. So there's evidence here that age is independently associated with the exposure. Now, there's nothing in the data set that's going to tell us whether age is part of a causal pathway linking the exposure to the disease. That's where our common sense, our prior knowledge comes into play. And we know that smoking doesn't cause age, and age therefore leads to heart disease. Age is this other factor causing a backdoor pathway. So it looks like in this data set, we would conclude that age appears to be a confounder. It satisfies those criteria in our definition. It's showing different age distributions, and it shows an independent association with the outcome, independently of smoking, say by just looking at the non-smokers. So that's how we can use this definition to detect confounders in our data sets. But there's an easier way to help us detect confounding based on statistics. And it comes from a second implication from that causal diagram. The causal diagram said there are two mechanisms that could explain why the smokers are getting more heart disease than the non-smokers. So when we measure the crude risk ratio, 2.0, that crude measure of association is reflecting both pathways. It's reflecting the effect of smoking and the effect of older age among the smokers. You'll find out as we go through this series of lectures that there are various ways we can control for confounders. We can block that backdoor pathway. I'm going to show you one in a minute. But if you block the backdoor pathway, you come up with an adjusted measure of association, which gives you an estimate of just that direct pathway, just the age-adjusted effect of smoking on heart disease. And you would expect if age were a confounder and you block the backdoor pathway, your adjusted measure of association would be different. So how can we use the data to help us decide whether a factor is a confounder? We can use this idea that if you control for a confounder and measure the association between the exposure and the outcome, if we look at an age-adjusted measure of association between smoking and heart disease, we should get a different value than when we didn't adjust for age, when we didn't control. So let's compare a unadjusted, crude measure of association to one that is adjusting for a potential confounder. And if really you have a confounder there, you should expect to see different values for the crude versus the adjusted measure of association. That's reflecting a necessary property of confounding. If something is a confounder and you control for it, you should get a different answer for your measure of association. You blocked a backdoor pathway by controlling for that confounder. It is a necessary consequence, implication of confounding. But unfortunately, it's not a sufficient property. It's not always true that if you did two analyses, one controlling for a factor and one not controlling for a factor, if you get different results, it doesn't always mean that you've controlled for a confounder. More often than not, it is because you're controlling for a confounder. So this alternative way for detecting confounding by comparing crude versus adjusted measures of association is often used as a method to detect evidence to support a factor being a confounder. And some people would use that as a second working definition. So going back to our study of smoking and heart disease, remember this is the first slide I showed you, comparing all 1,000 smokers to all 1,000 non-smokers. The crude risk ratio, as I mentioned, was 2.0. Well, what if we adjust for age? And we're going to do it using stratification, something I'll talk about in the next lecture. But for the time being, if you divide your data set, as we did, into two groups, just old people in one group, young people in another group, and let's suppose everybody in the old group is equally old. They're all 82 years old. You're comparing 82-year-old smokers to 82-year-old non-smokers. Age cannot be a confounder in this old group. Everyone's equally old. The non-exposed people are comparable to the exposed people with respect to age. Well, what's the measure of association? What's the estimated risk ratio in that old group? Well, the old smokers, there are 600 of them, 180 of them get disease. That's an estimated risk of 30%. The old non-smokers, there are 200 of them, 40 of them get disease. That's an estimated risk of 20%. What's the estimated risk of showing the effect of smoking among old people? 30% divided by 20% is 1.5, not the 2.0 we saw in the previous table. Well, what about the young people? Let's suppose everyone's equally young here. Let's suppose they're all 43 years old. 43-year-old smokers versus 43-year-old non-smokers. Smoking cannot be a confounder there. The non-smokers are comparable, exchangeable to the smokers with respect to age. What's the risk ratio among the young group? You got 400 smokers, 60 of them getting disease. That's a estimated risk of 15%. What about the young non-smokers? You got 800 of those and 80 of them get disease. That's an estimated risk of 10%. Estimated risk ratio is 1.5. So if I divide my data set into subgroups, young versus old, where the smokers and the non-smokers are exchangeable, they're comparable, notice I get a risk ratio of 1.5 in either case. I could say the adjusted measure, adjusting for age, in this case through stratification, something we're talking about in the next lecture, is giving me a different answer from the crude result. The crude result showed that the risk ratio was equal to 2. The adjusted result showed that the risk ratio is not 2, it's 1.5. You'd expect, if you're controlling for a confounder, to get different answers between crude and adjusted measures of association like we have here. So we could conclude that there's evidence here to argue that age is acting like a confounder. And this is another way, based on data, maybe a simpler way to detect evidence to support a factor being a confounder. So here are these two empirical ways for searching for confounding in your data set. One based on the definition, one based on the implications that a confounder should give you a different result if you control for it than if you didn't control for it. These two approaches are related to one another. The last one I compared, the change in estimate, comparing the risk ratio 2 for the crude analysis to the 1.5 for the adjusted analysis, there was a change in the value. 2 became a 1.5. That's reflecting the effect of confounding. It's a very practical way for detecting evidence in a data set that, in this case, age is a confounder. It's displaying the result of confounding. Because age was imbalanced, we got a risk ratio of 2, not a risk ratio of 1.5. It was bigger than 1.5 because the smokers had two bad things going for them. They smoked, and that increases their risk by a factor of 1.5, but they were also older, and that increased it even more to 2.0. The reason we got these change in values, these change in estimates between crude and adjusted analysis was because of confounding. Well, the definition we talked about, the conceptual definition, the confounder has to be related to the exposure and the outcome, is describing the mechanism for why we got those two different results. So there are two usually equivalent ways for searching a data set for deciding whether something is a confounder. And in most cases, they should lead to the same answers. Okay, Next thing I want to do is I now want to talk about how we actually do adjusted analysis. And I'll talk about stratification first. So see you next time. Bye.